Okay, good afternoon. So I was actually asked to talk about machine learning in CMS, and already Sharma has made my life much simpler. Already given 1.5 hours of talk on machine learning and discussed most of the architecture that are currently state of the art ML architectures. Okay, so what I will do is that I will actually start from more basic, probably, and we will have some overlap. And wherever there are some overlap, I have some slides, but I will probably try to skip them. Okay. So let me start with what we usually do in high energy physics. Is whenever we do some analysis, first thing is we try to perform some event selection. Right, means you want to look for some signal, but there are similar signals coming from other processes, and you want to first try to separate them out. Okay, so you define them like some events of your interest, which you call signal, and which are non-interesting to you, backgrounds, and you perform analysis to make other analysis to make some statistical statement out of this. Okay, so if you take some example, if you look at particle level, for example, you want to separate particles in the detector. So for example, you have some candidates and they can be electron, but pions can also fake as electrons in the detector. So you want to separate electrons from pions, for example. Or you have taus, which will come later. So taus will look almost like jets, okay? And jets, so jets can be misidentified as tau, lepton. So you want to identify what are actually the taus and what are the jets. Or if you want to have event classification, if this is object level classification, or it is event level classification. Suppose you want to have some signal like Higgs production, but the signature final state particles that you produce from Higgs process are also produced similarly in other standard model processes, and you want to separate those standard model processes from the Higgs or any new physics. Okay, so that's the kind of thing that you do before you make any statistical inference out from them. Okay, so how do you do that? Usually, if you don't use any machine learning, it's that you look at some distributions of major observables. Okay, for example, say these are the kind of distributions. This is from one process, this is from other process, or it can be functions of some different variables instead of just one variable. Okay, and then you see that whether these variables have good discriminating power, and then apply some threshold on this, or we call them the cuts, to accept or reject. So if you apply some cut here, you say that, okay, I accept these events as, say, electrons, and these events, say, pions. Okay, and this is what we call the cut-based selection. But when you do that, you have some contamination. So you actually not 100% pure. Okay, based on how much contamination you have, based on these cuts, you can know what is the efficiency and the fake rate. So you can define the efficiency, means the efficiency of events that fall above the cut for signal. Okay, so that defines your efficiency, and the ones that fall below defines your misidentification, or the ones of this kind falls here defines your misidentification probability. Okay, and based on this, you can actually find a ROC curve. So you can plot, you can scan the threshold X cut over here, full range, and find this curve. Okay, so for each cut, you find a point on this curve. So that will give you a curve of signal efficiency against the misidentification probability. Okay, so the better this curve goes this direction, the better is your separation. Okay, so 100% separation means it should be exactly like this. Okay, so that's called the receiver operating characteristics, or ROC. And the
distributions are apparently not well known, right? The background distribution.
If it is known, then only you can do this. Yes.
But they're very well constrained, because most of the time I get the background.
So when you design some experiment, I mean, when you design some analysis strategies, you use, say, Monte Carlo samples to model some background. But if that Monte Carlo sample doesn't actually describe the background correctly, then you have to use some data-driven method. Okay.
So supervised.
Yes. Yeah.
You completely
Rely on Monte Carlo samples. You assume that they actually model the background well.
About event generators.
Yeah. Yes. Okay. And sometimes, particularly in the event classification case, maybe the relative fraction of signal and background is not known. You want to actually estimate what is the relative fraction of signal. In that case, you actually use this problem becomes problem of parameter estimation. So, for example, the data describes like this, and your observable has two PDFs, background PDF and signal PDF. You combine them and fit to the data and estimate what is the total signal that I expect to have in my data. So that becomes parameter estimation. But then only if these are not well separated, then the estimation of alpha S or the parameter would not be very well. So if you have a better separation, the estimation or the uncertainty on the parameter becomes much smaller. You estimate it better. Okay. Okay. But then for one dimension, just if you have just one observable, or if you find some observable which is well separating the two classes, then it's okay to use cut-based. But then when you do not have such cases, for example, this is just for 2 dimension, here you have, say, the background distribution looks like this and signal looks like this, and you want to apply some cut-based analysis, you want to perform some cut-based analysis. So how do you choose the boundary of this? Okay. So the boundary, if you take simple cut-based like this or like this has much more contamination in the signal region. Okay. So you don't have really the cuts that you or the thresholds that you define are not well optimal. So how do you find actually an optimal cut? Okay. So if you look at, so there is a Neumann-Pearson lemma which says the optimal classifier is actually a cut on the likelihood ratio. The likelihood ratio, which is defined by the ratio of the signal PDF over the background PDF. Okay, any cut on this is the optimal classifier. But then how do you get these PDFs in multidimensional space? If you don't have a very well, one-dimensional PDF, then you don't know how to, you don't know how to find this. Okay, and it becomes more difficult. And if the variables are not correlated and they are independent, then you can write f of x as product of individual probabilities in each dimensions. But in often most of the cases, you see the observables are also correlated. Okay, so in this such kind of situation, it is the machine learning that actually helps. So the machine learning in this case, or for the classification problem, helps in estimation of this likelihood ratio using a limited training examples. So if we have a limited training examples of signal kind and background kind, and we have some observables, either low level or high level observables, we combine them. Each of these observables may be not well discriminating. Okay, so they are like weak classifiers, and you combine all of them together in a machine learning method, and you get a likelihood ratio, which gives you better classifier to classify these two class of events. Okay, so that's the idea why we opt for machine learning. Okay, instead of cut-based analysis, we try to find optimal classifiers to separate out two class of events, particularly in case of classification. Okay, so I can skip the machine learning. Just say what is the basic concepts about supervised learning. So supervised means you suppose you have some class of events and you have input data defined by some feature space features, and they are labeled. So you have their labels, okay, y1 to yn, and then you want to find a model which is basically a function which gives you, given the input features, and you get the function, it gives you a target prediction. And okay, and the idea of supervised learning is to find this model, okay, given the data and the labels. Okay. And yeah. So this function, in case of classification, can define or map this decision boundary between the two classes. Okay, and it won't be linear. So as is already discussed in the previous one. So we want to find a nonlinear boundary between the two classes, because often the boundaries are nonlinear. And in case of regression, this function maps to the true value of the actual underlying distribution. Okay, so given the measurements, you want to find what is the true value, okay, for each set of events. Okay, so what he has discussed mathematically, I am trying to discuss in few slides, maybe using pictures. Okay, so what artificial neuron does is the following. So you have input features, you have a set of parameters or weights, you multiply them, okay, as a matrix multiplication. Then you can add some bias term, which you can think like some feature with value 1, okay, and then you apply some activation and you get some output. So a single neuron just performs this, a simple matrix multiplication followed by an activation, okay. So if this activation function ideally should be a step function, because you want to separate signal and background, and you can label them as 1 and 0, and ideally it should be a step function. But if you use a step function, you cannot use it for learning because this is not differentiable. Okay, instead of step function, what one uses is a continuous function like this. So for example, in sigmoid case, you can use a sigmoid function which is 1 when x is sum is much higher than 0, or 0 when sum is much lower than 0. Okay, so then it defines two classes, and in between it is continuous. Okay, so you can use such a function which is differentiable to train this network. Okay, so there are many different kind of activation functions that he has said, and more often we use in the inner layers or intermediate layers, we use rectifier linear units or ReLU, and in the output, if it's a binary class, we use sigmoid, and if it is multi-class, it is often using softmax. Okay, so which gives you a probabilistic value of each of the classes. Okay, so again, what we had discussed, that if you just have one neuron, it doesn't give you a nonlinear, bounded function. So you need to add many neurons together, stack them, so that you get, in a layer-wise structure, then you get a nonlinear, function. So here you add them together, and then you can have, of course, if you have a binary class, then you have one output layer, which gives you 1 and 0, target value. Or if you have a multi-layer, multi-class, then you can have multiple output nodes. Okay. So given this network, so how you can train? Training means you want to adjust the weights in an iterative way, so that once it is trained, it is giving you the appropriate function to map the feature space to the target value. So that's the idea. So as you can see, if you change the weights by small amount, it changes the output, so that you can use this concept, which is called backpropagation. From given the output, we know how much error we made with respect to the true value, and from that we can change the weights in a direction in an iterative way, so that when this error is small, our weights are perfect to describe our model. Okay, so that's how it is done. So this loss that we define, usually ML uses two types of loss functions, but there are of course other types. So this is mean squared error, which is basically square of the difference between the truth and the predicted values. And you have also cross entropy. So you can actually mathematically show that both of them, when target value becomes same as truth value, both of them will vanish. Okay, and you can also show that if you use, particularly for classification, you use cross entropy, and for regression, you use MSc errors and use cross entropy, because you can show also mathematically that if you take a binary class, you can show that when you minimize the loss function, so you find a function which is monotonic to function of its ratio of the likelihoods. So that's the idea. So you actually find the function which predicts the ratio of the likelihoods. So that's the idea. Okay. So that's what you do. So if you take, say, one neuron, how do you change the weights? You change the weights as in the direction of the negative gradient of the loss function. So you change the weights by, say, delta W, some eta times gradient of delta L. Eta is the learning parameter that was said. And then you can show that if you do that, since delta L is proportional to this, okay? Yes. So then you can say that the change in loss function is always less than 0. That means every time you change the weights, the loss goes down, okay, towards the minimum. So it's apparently, you can understand that you can think, so this is in one dimension, you can think if you have multiple parameters, of course you will have many parameters in the model, and you can think this loss as a surface in multidimensional parameter space, and you start from arbitrarily from some point, and you, an iterative way, you start from somewhere, and then slowly you go towards a minimum. When you reach the minimum, you get the model which predicts your final states. Okay, so that was the basic thing that I wanted to say, and you already, you knew from previous lecture, at least mathematically. So what, as also as mentioned, that this, whatever we are discussing now, machine learning, and it has become a huge, research area. It was not new. So HEP used machine learning long back, so 1980s. So here is a, for example, one review paper in 1999 which says neural networks in high energy physics 10-year perspective. Okay, so and it was used in lab experiments and other experiments, and also in Higgs boson discovery, it played some significant role. Of course, it is not deep learning, but some level of machine learning, particularly the BDTs and ANNs. Okay, so but when we actually found Higgs boson in July 2012, the same year, this paper was published, and this called AlexNet, which was developed and participated in this ImageNet competition, and came out to be first. Okay, and now if you check this citation of this paper, I found it's something like 150,000 or more than that. Okay, so and the person, one of the author is one of the Nobel laureate, okay, who got Nobel Prize for machine learning. And this paper, I would say, actually revolutionized the deep learning applications. And after that, there are like huge competitions to develop different kind of algorithms. And of course, that was possible because we have also advancement in computing resources like GPUs and other things. Okay. Okay. So coming to CMS or LHC experiments, so you can see the history of how LHC experiments use this machine learning. So if you take round one was mostly using BDTs and NNs and doing simple classification and regression. Okay. Then round two started using it in reconstruction, calibration, high-level trigger, and even data quality monitoring. And round three, so we have now state-of-the-art frameworks which are used for data IMSc corrections, fast simulation, anomaly detection, level 1 trigger that we discussed. Even we are trying to develop machine learning to do particle flow. Okay, do a global event reconstruction. Okay. So I'll come one by one, okay, and some of them I will try to skip, which is similar. So first, the feed-forward neural network, so that we already discussed. So you can think, I mean, there is actually sort of a theorem. I don't know whether it is called theorem. It says that if you take feed-forward neural network, it can approximate any functions. But the only problem is that you will have to have many number of nodes, infinite number of nodes. Okay. Okay. And then this is the simple feed-forward network. And then you have also recurrent neural network, which is basically used for time series data like speech recognition, language translation, like that kind of this. Okay. So where you have kind of a short-term memory that is achieved by looping the output of the one-time step to the same layer again. Okay. So if you take an example of using this kind of network, so you can see one of the analysis, which is a challenging analysis, is looking for Higgs to BB in where Higgs is produced in association with top quarks. So the final state is very highly dense. So top decays to B quark and W, and then W decays to one of the W decays to lepton, one of the W decays to 2 jets. So you have like 4 jets, 1 lepton missing transverse energy. So that's very complicated final state. Okay. And you have a very similar background. So you have 2B coming from here and 2 top. So the number of objects in the final state is exact, except that the kinematics may be slightly different. So one have to explore these kinematic distributions to separate them out. Okay. So in this case, how it is done is uses a DNN. Okay. Also uses matrix element method and discriminant. Okay. Which is fed to DNN as one of the very observable. Then you categorize them into many categories. Okay. Based on what are the flavors in the final states, like even BB bars, B, C, and all type of jets coming from TT bar plus jets, and TTH. Okay. And this is categories into 36 categories. So the DNN categorizes them into 36 categories. Okay. So you can think like this. So you take all the inputs, and then you have 3 classes of events based on number of jets, and each class of events have a DNN. Okay. And each DNN again gives different predictions, different class predictions. Okay. So TTH, TTBB, TT plus light favor, and other ones. Okay. So you can take then the discriminator from each of these nodes, and then use them to fit, do a simultaneous fit, okay, to get the signal strength. So here you can see the distributions from one of the categories. So this is a category with more than 6 jets and more than 3 beta jets. So you can see that while the standard model background looks like this, the signal is expected to have more events in the high discriminant region. Okay. Okay. Now, CNN that has been discussed. So this is mostly used for image recognition, and also it is sensitive to translational invariant features. Okay. So the kind of applications that has been already discussed, like using it for flavor tagging, jet flavor tagging, and heavy boosted jet tagging, and so on. So here it's one of the results from CMS. So you can see this deep jet is based on this CNN, while deep CSE is based on this simple DNN. Okay. So you can see that compared to the deep CSB here, so the deep jet improves much more. That's if you look at the row curve. Okay. So if you take say simple same efficiency, the misidentification rate drops by at least factor of 10. Not 10, but yeah, 5, 6. Okay. Okay. So another one is the tau lepton identification. So tau is actually the only lepton. I don't know how many of you know tau lepton. So we have 3 leptons: electron, muon, and tau. Tau is the heaviest one, and tau lepton is the only one which can decay to hadrons, while muons, of course, cannot decay to hadrons, and electron doesn't decay. So if you look at the decay modes of the tau lepton, around 35% cases, they go to electrons or muons along with some neutrinos. But rest 65% of cases, they actually go to hadrons. But they have a distinct signatures. So either it goes to one charge hadron, and these charge hadrons are either mostly pions, charged pions, but occasionally also charged kaons. So it can go to one charge hadron or one charge hadron with pi 0 through a row meson, or one charge hadron with 2 pi zeros with a A1 meson as an intermediate particle, or you have 3 charge hadrons, okay? Or also 3 charge hadrons with pi 0. So there are five decay modes, and there are some other decay modes which is difficult to identify, okay, which is small fraction. So if you look at since they are hadrons, they will again, and coming from a decay of a heavy particle, so they will actually, and if the momentum of the tau is say like 20 GeV or so, so they will be moving in a cone, and this is actually a very narrow cone. So most of the cases, it is called a tau jet, okay, because it looks like a jet, a bunch of hadrons moving in a collinear way. So, but if you look at the shape of this tau jet with respect to the quark and gluon jet, there is a distinct feature that the tau jets with the decay products are actually very collimated. So they lie in a very narrow cone, okay, compared to the quark and gluon jets. So you can use this feature to separate out taus from jets. But then jets can be also very narrow occasionally, and the jet cross section is huge, okay? And because of that, even if you have very small fraction of jets misidentified as tau, you have a huge background. So one of the difficulties how to identify this tau and remove the jets as background. So initially, of course, we use BDTs to separate them out, but over years also developed CNN-based discriminator. So you can see as an image of the tau. So the image of the tau, you can see there is a narrow cone which contains the signal, and there is you can have a broad cone, okay, which can contain overall jet, okay. So this, but then there is other issues here. So when you have taus decaying to pi zeros, these pi zeros will decay to 2 photons, okay. These photons will actually can deposit energy in the calorimeter, electromagnetic calorimeter, but occasionally these photons also will convert to E plus E minus, and in the magnetic field there's very low PT E plus E minus, they move away from each other. So there is a elongated strips. So energy is spread over large distance. So occasionally they can actually move away from this cone, okay. So what is done is that it's taken 2 different cones, okay. One around the direction of the tau, smaller cone, and one bigger than this. And each of them, this one is divided into very small cells, and this one is divided into bigger cells of size 0.05 times 0.05, while this is 0.02 times 0.02 with same, and then fed them to a CNN, okay, along with some of the high-level variables. High-level means the ones you can reconstruct, okay, from the detector, like its decay number of particles, their momentum, and as well as, like we discussed in case of BJets, there is a decay vortex, okay. So similarly for tau case, since tau is also have a higher lifetime, okay, so they will also travel certain distance before decay. So you will also have a secondary vortex, and you can also find what is the corresponding decay length. All of these can be combined together in this case, okay. So this is taking high-level features, and these are taking the low-level features of individual particles inside these bigger and smaller cones, okay. So they are combined together, and then they are passed through a CNN. And the output of the CNN gives you a probability. So 4 different probabilities: probability to become tau-like, or probability to become jet-like, or also it can be electron-muon. In fact, if you look at this one, so if you have an electron, they will also deposit energy in the electromagnetic calorimeter, and electron can perfectly fake a single prong tau. So you need to separate them out. So this discriminator separates out to taus from 3 different objects, okay? Jets, muon, and electron. Okay, so you can see how much it is improved. So from cut-based method using a boosted decision tree, it was improved by this much. So for same efficiency, the fake rate was reduced by a factor of 2. Then using this CNN-based method, you get another factor of 2 reduction in the fake rate. Okay. And further, it was found that since, as initially we were discussing, if the Monte Carlo sample doesn't model the data very well, then the model that you generate, ML model that you get doesn't describe data very well. Okay, so this discrepancy can be there. So we found some discrepancy in this case. Okay, so in a very high score region, the data and Monte Carlo doesn't match very well. Okay, so in order to do this matching, additional thing was added to this. Okay, so something called domain adaptation. So you can add a adversarial network to the existing network, and the adversarial network actually competes with this network and tries to discriminate between data and MC as much as possible. Okay, so by adding this, you try to model MC more and more close to the data. Okay, so you can see after this, using domain adaptation, the data matched to Monte Carlo much better than what it was previously. And of course, there are some improvement also happened due to this. So you can see that with respect to the previous version, it improved further, the ROC curve. Okay. Okay. So again, some discussion was there about the trigger. Okay. So yeah. So as you can see we have 2-stage trigger that was discussed. So level 1 and high level. So although level 1 is difficult to use because at this point, okay, but machine learning has been used in the high level trigger since round 2. Okay, so at least the shallow networks. But you can see that for the tau case, so initially in the round 2, we use the full cut-based methods to reconstruct the tau, because you have to process the event within a few milliseconds. That's the timing constant. Okay, so if you use a model which doesn't process, and it depends on also available computing power. So in the round 3, the computing power also improved because we started using GPUs in the trigger level, and then some other improvement happened, like having a GPU-based reconstruction of the tracks, which is needed for doing machine learning. Okay, so then in the round 3, so you added neural network-based tagger. So this is a CNN-based tagger at this level, and also the offline algorithm that we discussed was also added at this level. Okay, so doing that, you are able to improve at least by a factor of 10 and efficiency about 10% or so. Okay. Yeah. So this picture you have seen. Yeah.
Improvement of efficiency was mostly around 50 GeV-ish, whereas there is also a slight improvement in, say, 1 TeV or 2 TeV, but mostly from the low PT regime, the efficiency.
Yeah, so because high PT regime, they are clean taus. High PT regime jets, when you have high PT, they are also very well collimated, so the tau is identified much better. But when you have low PT, it is the jet fakes more. So then to reject them, you put tighter cuts.
No, like we sort of put this as a conjecture, but in the object groups, are there tests of resilience that in a simulation, if you sort of around 70 GeV, throw away the contaminating materials, like the whatever is coming, whether or not the efficiency improves or not? Like, is there a direct cross-check of these answers that in low PT region, there are more additional stuff apart from the hadronic tau, which is contained?
Yes, so what happens when you have low PT, the tau is actually a bit broader. And then also this, as I said, when the photons go to converted electrons, they are also low PT. So all of them makes a wider cone and then mixes with the isolation particles coming from jets. So because of this, so you are basically, and when you put quartz, so it becomes tighter for them and it rejects, it reduces the efficiency. So, but high PT, it is much easily reconstructible. And machine learning actually in this case helps at low PT so that you can recover those objects. Okay, so again, boosted and merged objects, we discussed about the W, so you can also see how it looks like for a top. So you see a three-pronged structure here, and yeah. So initially we had deep AKH, which is based on the CNN, okay? And you can see deep AKH performance, which is blue, so it is here, okay? The ROC curve. Okay, so another thing is this analysis, which is, you can see a Higgs decays to two pseudoscalars, where these pseudoscalars are very low mass. So in some model it is possible, okay? And we are trying to chase all possible models because we have not seen any new thing yet in LHC apart from the Higgs. So this kind of model here, the A is about 1 GeV or smaller. So since it is 1 GeV or small, up to 0.1 GeV, so in that case, this A is very highly boosted coming from the Higgs because Higgs is 125 GeV. And because of that, these two photons will be almost merged, okay? So they are not separable. So you can see different cases here. So when mass of A is 1 GeV, you see the two photons very close to each other, very overlapping, but maybe slightly less overlapping, okay? When you go to smaller mass, like 0.4 GeV, so or 0.1 GeV, it's almost like a just single photon. So they are completely 100% overlapping with each other. So you are not able to reconstruct with traditional methods. You will not be able to reconstruct these two photons separately, and you will basically identify them as a single photon. And if you identify them as a single photon, you won't be able to calculate their mass, okay? So you won't find the mass of the A. So one of this analysis was possible only because we now have machine learning. If we did not have machine learning, it would not have been possible. So they use a end-to-end ML-based particle reconstruction. Usually in CMS, you reconstruct particles and then use machine learning and so on. The low-level particles are reconstructed using particle flow. In this case, they simply use the energy from the ECAL calorimeter. So you can see the calorimeter size of the crystal size is in centimeter or millimeter. It's 22 millimeter times 22 millimeter, which translates to eta phi as 0.0175 times 0.0175. Okay, so that shows size of the crystal in eta phi. Okay. But here it actually shows in terms of index, not in really, in this radian. So that's why, so you cannot actually, both the photons will go to same crystal. Only the leakage part will go to other crystals. So basically you cannot separate them out, okay? In any way you try to do. So they use this network architecture called ResNet CNN, okay? And what it does is it takes the calorimeter image, okay? And it processes all the information from here as well as the track, if there is any tracks and so on, because it can be coming from electrons and so on, because there is conversions. And then it predicts directly the observable that we need. That means the mass of the A boson, okay? So the output is the regressed mass of the A boson, okay? So you can see the results from this analysis. So if you use traditional methods, try to reconstruct photon. So they validated this using a pi0, because you need to have a standard model candle to see that the reconstruction technique that you use is actually validated in data before you apply to something unknown. So if you try to reconstruct a pi0 where pi0 is very highly boosted, then you will not be able to reconstruct its mass. So what you will get is like this. Okay, so this uses 3x3 clustering, which is one of the clustering method for reconstructing the photons. Then even photon neural network, which tries to identify individual photons, that also failed. So, but this analysis, which tries to identify diphoton, not just a photon, so it assumes that this is a diphoton, not for single photon. So using that method, so you are able to reconstruct the pi0 mass, which is 137 MeV. Okay, and so they performed this is the first search of this kind in CMS. So they performed this analysis and going down to 0.1 GeV. Okay. Second thing is graph neural network that discussed. So again, you can see the further improvements with respect to the CNN-based networks here. Okay, CMS trigger system already discussed. So I discussed the high-level triggers here. So the high-level trigger basically uses the computing farm. That's why we are trying to use ML method for them at the moment. But of course, there is a development to do at the level 1 case. So you can also see the improvement of the B tagging at the HLT. So you can see that particularly that he discussed about the double Higgs production. And double Higgs production, the most important channel is 4B, okay, along with, of course, 2B, 2 gamma, and 2B, 2 tau, because they get high branching fractions. And without machine learning, you get this efficiency. Here, every drop of efficiency is very important because we want to collect as much as data so that we can, see the 2 Higgs and production, and also, measure the self-coupling parameter. So with this, again, particle net 1, so it has improved up to this yellow. So you are able to get much closer to 1 now, okay, at the trigger level. And particle net also simultaneously can reconstruct tau, okay. So you can see with respect to the CNN-based tau at the high-level trigger, the particle net further improves. This comes from particle net. So if you choose a working point here, you can see much higher reduction in misidentification probability for the same efficiency. Okay. So for the transformers case also, as there is we have now this U-part and GLOW-part, algorithms. So you can see over time with different methods coming from DNN, then CNN, graph, then transformer based. So over the years, you can see how the improvement happens. So now the latest state of the art is this transformer based one, which gives better results. Okay, and you can also see the CZ rejection with respect to the BZ. It becomes more and more. So you reject more and more CZs. But in addition to that, it also can do C tagging simultaneously. So it does B tagging, C tagging, tau tagging, and S tagging simultaneously. So now, as you are discussing now, because of this, you are able to see also Higgs to CC bar, okay? Or will be able to see very soon. Yeah, so also we are, able to identify taus. So this is for the tau, this is for the SZs, and this is for the tau leptons. So you are getting better and better in both cases. Of course, as in S case, you have much higher take rates. Okay, so I'll take 5 more minutes if possible. Okay. Yeah.
For the strange tagging, there is still no information of timing has been used, right? So in future runs, that may improve.
That may improve, yes. Yeah. So one of the things that is being studied, particularly aiming for high luminosity LHC, because high luminosity LHC will have 140 additional PP interactions or pile up. Currently, we have about 60. pileup events. Okay, so when you have 140 to 200 pileups in high luminosity LHC, the current particle flow algorithm, which is rule based, okay, just does iteratively reconstructs each particles, will not be able to scale it to that level. Okay, and it will be much more slower. Okay, so instead of that, CMS is trying to develop machine learning based particle flow. So currently the architecture uses a transformer based one, and it, instead of iteratively predicting individual particles one by one, it tries to predict all particles simultaneously at one inference step. Okay, so while this is going to benefit high luminosity LHC and targeted for that, it is already being developed and validated in using the RON3 data. So the usual particle flow or particle flow concept that you take the particles when they go to detectors, you basically deposit all the energies in the detectors, so you get basically detector energy deposits. From this, the algorithm tries to reconstruct back individual particles. It's like a global event reconstruction. Okay, and then you can use these particles to make jets, taus, everything, which is currently being done. And this is one of the reason the jet resolution is better at the moment. If you use simply these ones, the jet resolution will be much poor. Okay. So you can see what currently already have. So they have used, for example, you can see from the TT bar events. So this is without pileup. So the distribution of number of particles as a function of PT. So you can see that these are from the generated particles, okay, and the particle flow is a cross, and this one is dots. Okay, so you can see that the dots match better to the generated particles compared to the particle flow, so the efficiency also improves. Okay, so that also you can see from this plot. So the efficiency is coming closer to 1, particularly in the neutral hadron case. And if you then cluster them together, those particles, then form the jets, then you can see that the PF and MLPF both are pretty similar. Okay, but in terms of the response looks similar, but when you look at the resolutions of the jets, the ML based one has a better resolution compared to the traditional ones. Okay, so you're already starting to improve. Okay, so the last one is anomaly detection. So we are at the trigger level, we take data, and as we said, if we lose data, if our trigger doesn't select some interesting data, the data is lost. So we do not have that data to look at some future result. So suppose we have some models or something that is actually there, but somehow we did not manage to know that model yet and did not design the trigger. Okay, then that we did not manage to collect them, even if we have produced so many of events in LHC, and we have lost it. So to counter that, so CMS has developed 2 anomaly detection triggers. Okay, so the anomaly detection is concept is like this. So you take a piece of data, okay, you compress it using some machine learning framework, and then you decompress them, okay, and find whether you get the same data or not. So you reduce the latent space, and then you expand them again. So if it is, when you train it, so it learns to predict the same data, okay. But if there is some different data it has not seen, it won't be able to predict that, okay, same data. In that case, the loss function between the two will be much higher compared to the ones which were used for the training. So that's loss function you can see to see whether they are same type of events or some anomalous type of events.
The meaning of compressing the thing.
So, for example, you have say 10 feature space. Okay, feature space is size of 10. Okay, 10 number of variables. Then you have 10 nodes. When you reduce the number of nodes, so you basically compress, information is compressed. So at the end, maybe you have few nodes, 3, 4 nodes. So the information that you started with is compressed, and then you try to expand them. Okay, decompress them. So that's the idea. Okay, so it is used at the level 1. So there is two algorithms. One is cicada, which comes from colorimeter image convolution anomaly detection algorithm. So it takes the low level inputs from the level 1 colorimeter trigger and uses it. And another one is called AXO, which is taking all globally reconstructed candidates from level 1 trigger. Okay, so both muons as well as colorimeter jets, taus, and everything. So the AXO one uses a variational autoencoder, which is a generative model that was discussed, and compress this data, and then you use the score defined or loss defined as this as the score of this algorithm. So you can see some results. Of course, you cannot say whether it got any anomaly events or not unless you analyze this. So to validate that, they select interesting events. They look at the diamond mass spectrum from events selected by this anomaly detector, and you can see it is able to get the peaks like G2 mu mu, or this is, I think this is epsilon to mu mu. Okay.
First peak was Jepsi.
Maybe Jepsi. Yeah, Jepsi. Around 3. This is around 3 GB, right? Jepsi is around 3 or 4. 3. Yeah. Okay. Then another one is cicada. So this is again the same thing, but it is just a convolutional neural network based autoencoder. So both sides you have convolutional layers. Okay. And you can see the scores from a zero bias event, which is used for training, you get much smaller score. Okay. While if you test it with a Higgs signal, for example, so you get a much higher score from this. Yeah, okay, that's it from my side. So I tried to give you some results from CMS, but of course it's not extensive. So there are many more there. Yeah, that's all. So I think in future we'll have more and more use of ML methods in analysis.
Yeah. Thank you. Yeah, it gives us an idea that how in machine learning how in high energy physics we use machine learning. So yeah, please, any question? Very quick. No? Okay, thank you.